In this video, I want to look at something called radial vector fields. There are some key properties or characteristics of radial vector fields that are going to be important to us when I move forward with the kinds of problems we can solve with calculus of multiple variables. The key characteristic of a radial vector field is that all the vectors point directly toward or away from the origin except at the origin itself. This means that they are all aligned so that they are parallel to the position vector given by r is equal to the vector xy. Radial vector fields show up quite frequently, and they have some wonderful symmetries, provided we're comfortable with working in cylindrical or spherical coordinates. If I let r equal the vector with components xy, a vector field in the form of the vector f is equal to f of xy times r, where f is a scalar valued function, is a radial vector field. Radial vector fields that have the form f of xy is equal to r over the magnitude of r raised to the p power, which is the same thing as saying the vector xy over the magnitude of r raised to the p power, where p is a real number, are vector fields where the vectors point radially outward from the origin with a magnitude that is given by the magnitude of the vector f is equal to 1 over the magnitude of r raised to the p minus 1 power. Now, if we consider p is equal to 1, we just end up with a unit vector. If p is equal to 3, the vectors will decrease as they get further away from 0. This is a significant characteristic to consider because p is equal to 3 comes up frequently when I'm working with problems that involve central forces, where the force felt by a particle will follow the inverse square law, F is equal to 1 over r squared. There can also be what we call a rotation field. While radial vector fields point directly toward or away from an origin in all directions, a rotation field will be composed of vectors that are tangent to a curve at each point. So an example might look like sets of vectors that form a circle around the origin of my coordinate system. And one of the things that is important to note about rotation fields is that there's going to be a direction, either clockwise or counterclockwise, to these rotation fields. And the kinds of vectors we're working with will determine the direction that a rotation field has. It also means that a radial vector and a rotation vector will be orthogonal to each other at all points. So let's work an example. I want to determine the points, if any, on the curve C defined by all the points xy, such that x squared plus y squared is equal to 1, at which the vector f is equal to the components y and negative x, is tangent to C and normal to C. Sketch C and a few representative vectors of f. The first thing I note is that C is a circle of radius 1 centered at the origin. So I'm going to construct a coordinate system, then I'm going to construct my unit circle. Now I'm going to parameterize x and y. X is equal to 1 times cosine t and y is equal to 1 times sine t. And if del g of xy is equal to 2x plus 2y, I can take the derivative of del g using my parameterized values. D by dt of the vector with components 2 cosine t, 2 sine t becomes the vector negative 2 sine t, 2 cosine t. When I do a little bit of algebra with this, I get x is equal to negative y and y is equal to x. So a vector tangent to the curve at the point xy is given by a vector with components negative y, x. Since the vector negative yx is equal to negative 1 times the vector y negative x, the tangent vector and f are scalar multiples of each other, meaning that they are parallel at all points xy. This tells me that my vector f is tangent to the circle at all points. Some of my sample vectors include a vector in the clockwise direction in quadrant 4, a vector in the clockwise direction in quadrant 3, a vector in the clockwise direction in quadrant 2, and another vector in the clockwise direction in quadrant 1. And all of these vectors are tangent to my unit circle. Now you get to try it. Pause the video and determine the points, if any, on the curve C is equal to the set of all points xy such that x is equal to 1, at which the vector f given by the components xy is tangent to C and normal to C. Sketch C and a few representative vectors of f. When you're ready, restart the video to check your understanding. So I set up my coordinate axes and I note that the curve C is a straight vertical line through the point x is equal to 1. So I simply draw my vertical line. This means that all tangent vectors of C will have coordinates of 0, y, and they will lie directly on that line. It also means that my vector f cannot be a scalar multiple at all points because x is equal to 1 at C. If I look at the dot product of the vector xy dotted with the vector 0y, I get y squared. This is 0 when y is 0. This means that f is orthogonal to C at the point y is equal to 0, and I can sketch that vector on my graph. It simply lies along the x-axis pointed from the line C to the right. I'm going to put in a few more representative vectors. There's a vector in quadrant 1 above the x-axis that points up and to the right, extending to the right from my line C. There's a vector in quadrant 4 below the x-axis that points down and to the left, also extending to the right of my line C. There's also a vector in quadrant 4 that points down to the left that is slightly smaller in magnitude, and it sits to the left of my curve C. And there is a vector in quadrant 1 to the left of my curve C that points upward to the right, again with a smaller magnitude than the vectors that lie to the right. This is how I can use the concepts of a radial vector field and a rotation field to be able to determine where my vectors might lie with respect to whether they are orthogonal or parallel to a given curve at any given point. Be sure and let me know if you have any questions about working with these radial and rotation field ideas.